company called United Launch Alliance. They've been working for a very long time, have had many different rockets with no failures, and they're kind of the traditional go-to rocket company. On the right, we've got SpaceX. Who has heard of SpaceX? OK. Just want to check. So SpaceX on the right, new upstart with building rockets, actually been around for quite a while now, but at this point they're starting to get the cadence to be going up, and to have reusability, things like that. So pretty important there. This is just showing a bunch of different other types of rockets. There's actually lots of different rockets that are available from different countries, and there's probably not much reason for us to go into that at the moment right now. Some current, upcoming, and existing innovations in launch. So launch sucks. You're basically expending this chemical energy in order to put us to the orbit. But back on these rockets, so the payload is actually like this, and then your rocket is this. And that's because of something called the rocket equation. The rocket equation, and it's exponential. So you have an exponential, and you have a tiny little mass divided by your total mass. And that determines the amount of delta V that you need, change in velocity, which, as I said, was 8,000 meters per second, which is a relatively big number to be putting into that exponential mass fraction. As a result, even with a staged rocket design, you're looking at getting maybe 10%, probably more like 5% of the rocket's total mass is your payload. So this is a problem. There's not a huge amount, and beyond that is we have to throw the rocket away every time we use it. And so as Elon has put it many times in public description, it's like every time you want to drive somewhere, you toss the car after you use it. Or every time that an airline flew somewhere, it would just send the plane to the junkyard after it uses it, which is unfortunate, which is why he's been going and using reusability, which actually managed to achieve by landing the first stages, landing the Dragons, potentially even landing the fairings that are around the satellites as well. In the middle, I just got a picture of one of these nano-launch rockets. And on the right, have something called Skylon, which is it's a company called Reaction Engines. And they're looking at building air-breathing propulsion, meaning that they actually use a jet, kind of like what aircraft use. And that's how they get a lot of their delta V, using the air. So the reason that an airplane is so much more efficient than a rocket is that a rocket has to carry both the fuel and the oxidizer with it, whereas an airplane only carries fuel, just like your car does. And then the oxidizer is that it pulls in oxygen from the atmosphere and uses that. Now, the oxygen tends to be, A, very not all that dense, and B, kind of abundant. So if you're able to just burn your fuel like an airplane does and then pull in oxygen, you can be way more efficient. Now, as you get higher and higher, there's less oxygen, so that becomes not a viable strategy. But there's some concepts that people are looking at, which I personally think is kind of the way of the future once we get there for launching things, to get as much as you can initially by using the atmosphere to give you oxidizer, and then switch over to traditional rocket mode once you get higher. But hopefully you've built up a lot of your energy by that point. Go a little bit into some of the different challenges of rockets or of the space industry in general. So one of the things is regulatory emissions. So in geostationary, when you're in the geostationary arc, it's very regulated what frequencies you can be using and where you can be beaming different frequencies to the ground. As we said before, you're going a very long way. As a result, receivers need to be very sensitive. And because of that, you need to make sure that you're sufficiently outside of any frequency bands that you're not interfering with somebody else. So there's an organization called the ITU, which regulates these things. It's actually a very big deal. It's almost like kind of like buying web domains in order to get access to these. People like grab them, and then they'll swap them, and then they'll have them kind of for time. Something called ITAR, International Traffic and Arms Regulations, and EAR, Expert Arms Regulations. This is a big issue. This is the result of frankly, US government thinking that a satellite is the same thing as a cruise missile, and therefore being afraid of any sort of technology that goes into a satellite, resulting in other countries learning how to build cruise missiles. So it's really silly, but it's a really big deal for companies that are building space hardware in the United States, because it means that you have significant restrictions on people that you can hire, and it means that you have significant restrictions on components that you can buy, what you can talk with, what rockets that you can use, and what sort of exports you can do. Environmental extremes, like we talked about before, the components in space will get very hot, very cold. When you launch something, the environment is very extreme. It gets shaken really hard. So being able to design around these sorts of things is very challenging. Radiation, the Earth or humans have evolved within the Earth, within the protective shell of the ionosphere, which has allowed us to become who we are, and allowed us to shield us from a lot of the sun's radiation, or galactic radiation, or total background radiation. Once you're outside of the magnetosphere, you no longer have that anymore. As a result, you have to deal with a lot of that. And the components that you're used to, that we have built to work in Earth, don't necessarily work up there either. As it turns out, a lot of components actually do, and that's one of the kind of new things that's been coming up lately, is learning how to use those components and figuring out which ones will work in space, which ones will not. Jumping ahead, looking a little bit at the future, what are potential things that are coming up? To kind of get your brain juices flowing of what, if we want to get involved in space, what might be coming up next. Some of these things are mining asteroids, building habitats in orbit, building habitats elsewhere, finding reasons to go and live on Mars, making that economically viable. The biggest challenge to all these things is, A, that it's really hard to get there, really hard to put enough hardware there and be useful. But there is actually a great deal of promise of potential things that we could achieve with sufficient technology.